Welcome to the second video on Vsepr. Remember, in the first video, we saw what happened when you had 2, 3, or 4 electron groups on that central atom. In this video, we're looking at what happens when you have 5 or 6 electron groups on that central atom. So here, again, you should be looking at your Vsepr tables that have been printed out from the PowerPoint. This is a continuation of that first video. We went through 1 through 4 on the first video. Now we're looking at 5 and 6 electron groups for this video. So 5 electron groups. I'm going to build our first molecule. Our first molecule is PCl5. When you look at the Lewis structure for PCl5, you're going to see you have 5 bonding groups, no lone pairs. So 5 total electron groups, 5 bonding groups, no lone pairs. Let's go ahead and build this molecule. First thing you want to notice about this particular molecule is this one is not perfectly symmetric along each of the axes. Some of the ones we saw before, actually all the ones we saw before, had symmetry running everywhere, meaning all of those outer atom positions were identical. In this one, that's not true. If I kind of rotate this molecule around, you're going to see that there are some distinct positions in here. These 3 around the middle are very different than these 2 kind of on the ends. And you're going to see that when we show the bond angles. Being there's a distinct difference between these 2, the one that's up and the one that's down, versus the ones that are here in the middle, we call these 2 different positions by different names. You want to be familiar with these names. If you kind of think about this as a globe, it kind of makes it a little bit easier to deal with these names. These 3 in the middle, well, if this were a globe, that'd be the equator. So these are often called equatorial positions. Meanwhile, the 2 at the top, the one at the top and the one at the bottom, kind of run through the axis of this shape. So we call these 2, the top and the bottom, the axial position. So we have 2 different positions. We have these 3 in the middle that are equatorial positions, and these 2 on the top and the bottom that run through the axis are called the axial positions. This is how the molecule looks in 3 dimensions. Definitely no chance of your 2-dimensional Lewis structure looking like this. So this is where you really want to step beyond what you're seeing in the 2-dimensional Lewis structure and actually start thinking about these molecules in 3 dimensions. So let's start talking about the different properties that we're looking at for this. So first, kind of the name for this positioning of the 5 electron groups. Remember, the electron groups are the sticks here. So this electron pair geometry we call Trigonal Bi-Pyramidal. So let's talk a little bit about that naming. What you want to imagine is everything in the middle here is trying to form a base of a pyramid, and it would be a triangle-shaped base. It's not just a pyramid pointing up, though. There's also a pyramid pointing down. So that's where we get the bipyramidal from. So this is trigonal bipyramidal for this electron pair geometry. For the molecular geometry, again, no lone pairs. So if I don't have any lone pairs, as we saw in the previous video, no lone pairs means that my molecular geometry will match the electron pair geometry that we have here. Now for this molecule, we actually have 3 different bond angles that we're seeing in this. Okay, so I want to point out all of those bond angles. Everything previous, we were only looking at 1 bond angle for each thing. Here we're looking at 3. If I try to show these bond angles as they're happening, first, now I'm kind of looking at a top-down view. All the ones on the equator are 120 degrees apart. So now it's like we're looking at the very top of the molecule going straight down the axis. We have 120-degree bond angles. What we also have, reposition our molecule a little bit here. What we also have is if you look at the angle between an axial outer atom and an equatorial outer atom, you're looking at a 90-degree bond angle. And the one that's not listed here but is still present, you need to make sure you have it, is that 180-degree bond angle between axial and the other axial. So here we end up with three different bond angles: 90-degree bond angles, 120-degree bond angles, and 180-degree bond angles. Again, we're going to skip the hybridization for right now. We'll do that and go back and cover hybridization in a separate video. But we want to talk about the polarity of this. The first thing we want to notice is, does everything cancel out? And if you've been following along with our other shapes, you can kind of use that to help out if will everything cancel out. So the two axial positions, if all the outer atoms are identical, then these two would cancel out. Now, will the three equatorial positions cancel out? Well, if I move my molecule now, I can see that these three outer atoms in the equatorial positions are all identical and completely evenly spaced out. So this would be nonpolar here as well for the equatorial. So everything would still cancel out in this molecule, and we'd be left with a nonpolar molecule. Anytime you have 5 electron groups, your base electron pair geometry will be trigonal bipyramidal. Let's go ahead and remove everything here so we can build our next molecule. Our next molecule we want to build is Sf4. And so you see the Lewis structure for Sf4. Here, you're counting up the total electron groups. There's 5. There's 4 bonds and 1 lone pair. So we have 5 total electron groups, 4 bonding groups, 1 lone pair. So let's build that molecule. I need 4 bonding groups, and now I have a lone pair. I'm going to reposition the molecule so we can kind of look at it in a very specific way that'll help identify some of the shapes that are going on here. First off, 5 electron groups will always be trigonal bipyramidal. If I kind of show that trigonal bipyramidal arrangement here, you can see everything's still arranged in that trigonal bipyramidal arrangement. Notice where the lone pair goes. Remember, before, when we had 2, 3, or 4 electron groups, it didn't matter where the lone pair went because everything was symmetrical. Here, there's 2 different positions. There's axial positions and equatorial positions. And what you see is that the lone pair is going into an equatorial position. You're going to find all the lone pairs will go into those equatorial positions because that spaces out the lone pairs to the greatest degree possible. So our electron geometry is still trigonal bipyramidal. Now let me rearrange this such that you can see the actual molecular geometry. And if you kind of look at this, you can kind of see it kind of looks like something you're a little bit familiar with. The molecular geometry for this is the seesaw. You can kind of see a seesaw like pattern here with one side going up, the other side's going to go down in this. So it's like a teeter-totter. Seesaw is our technical name for this specific molecular geometry. If we're looking at the bond angles that we have here, we still have the 90s, the 120, and the 180. I want to kind of go through and show you all of these bond angles. First thing is that we still have those 90-degree bond angles. If I rotate the molecule, you can see between axial and equatorial, I still have some 90-degree bond angles. What I also still have is between the 2 equatorial positions, I still have a 120-degree bond angle. And lastly, the simulation doesn't show this, but one you don't want to forget about is you still have that 180-degree bond angle between the 2 axial positions. So we're still going to skip our hybridization, come back to that later. I'm going to talk about if this molecule is polar or nonpolar. So if we're looking at this being polar, nonpolar, we just have to answer a simple question: will everything cancel out or not? And here, the two axial positions would cancel out. They're equal and opposite. But if I look at those equatorial positions, they're not equal and opposite. They're equal strength, but they're not situated opposite of each other. So being they're not situated opposite of each other, this specific molecule will end up being polar. So that's what we're looking at when you have 5 electron groups, 4 of which are bonding, 1 of which is a lone pair. You get this seesaw molecular geometry. So if I clear everything off, so we can build our next molecule. Our next molecule we want to look at is ICl3. And when you're looking at the Lewis structure for this, you're looking at 5 electron groups. Of those 5 electron groups, 3 of them are going to be bonding groups, 2 of them are going to be lone pairs. So let's go ahead and build ICl3. I need 3 bonding groups, 2 lone pairs. So first, let's talk about that electron pair geometry. You can see the electrons are all situated still in that trigonal bipyramidal electron pair geometry. Go ahead and select it. Trigonal bipyramidal. Everything's still set up for that. In terms of molecular geometry, remember the molecular geometry, we are just looking at how are the atoms situated. So I'm going to move the molecule so you can kind of see where they get the name for this molecular geometry. Remember, the molecular geometry is just where the atom's situated, and you can see it kind of looks like a T. And being it looks like a T, we end up calling this T shape. Now for our bond angles here, here's where you got to be careful. Remember, that trigonal bipyramidal arrangement for the electrons gave us 3 possibilities that we've seen so far for bond angles, 90, 120, and 180. Here, if I show some of the bond angles, we still have those 90s. Outer, central, outer is a 90. Outer, central, outer is a 90. And we still have the 180 from here. But what you're going to notice is no matter how you turn the molecule, I don't have that 120-degree bond angle anymore. The reason I don't have that 120-degree bond angle is remember where that 120-degree bond angle came from. It came from 2 outer atoms on the equatorial position. Well, here I only have 1 outer atom in the equatorial position. I don't have that second one. So I no longer have that 120-degree angle anymore. Another way of thinking about it is called T-shaped. There isn't a T out there that has a 120-degree bond angle. The angles in a T are 90 and 180. If I reposition this kind of more into that T shape again, we can talk about whether this will be polar or non-polar. T-shaped, even if everything is the same, has to be polar. The reason why? These 2 positions, the one I have left and right, those axial positions would cancel out. There's nothing to cancel out this one at the bottom. So this one would end up being a polar molecule. If I go ahead and take everything off of this, we can build our next molecule. Our next molecule is going to be an example, XEF2. Now, we've talked about noble gases not generally forming bonds very often, but this molecule represents one of those exceptions. Some noble gases can form bonds with other atoms. Turns out those larger noble gases like krypton and xenon farther down on the periodic table can form bonds sometimes with the halogens. So that's what we're seeing here for XEF2. So if you look at the Lewis structure for XEF2, you're looking at 5 electron groups, 2 of which are bonding, 3 lone pairs. So I'm going to put in our 2 bonding groups. Put in our 2 bonding groups, and now I'm going to put in 3 lone pairs. So you can see for the electron pair geometry, where are the electrons situated? And the electrons are still situated in that trigonal bipyramidal geometry. So our electron pair geometry still hasn't changed. Anytime you have 5 electron groups, you should be looking at a trigonal bipyramidal electron pair geometry. Well, now we can actually start talking about the molecular geometry. Well, for the molecular geometry, I'm just looking at the atoms. And right away, I can rotate the molecule to help see this. You're looking at the atoms. Well, they're in a straight line. Things in a straight line we would call linear. So this is a linear molecular geometry. If I show the bond angles, there's only one bond angle here, and it's 180 degrees. In linear, you have to be looking at 180 degrees. So here, for whether this is polar or nonpolar, because both of these outer atoms are identical, they're both fluorines, and because they are equally spaced apart, 180 degrees apart from each other, their poles will cancel out. So being their individual poles will cancel out, this one would be nonpolar. But remember, here's where you have to be careful. Imagine if one of these outer atoms was something else. Imagine I had one fluorine and one chlorine. Well, if I was in that situation, though, then this molecule would be polar, because even though these are equally spaced apart, they don't have equal poles, with fluorine being more electronegative than the chlorine. So you really have to analyze the specific molecule that you're looking at for this. So that one is the last in the sequence of things that have 5 electron groups. Our last set of molecules are things that have 6 electron groups. So I'm going to go ahead and clear everything off so we can look at what we have for 6 electron groups. So for 6 electron groups, again, definitely an expanded octet again, we're looking at something like Sf6. So if you're looking at the Lewis structure for Sf6, you're going to see 6 electron groups around that central atom. All 6 of them are bonding groups. There's no lone pairs. Let's go ahead and build this molecule. So I need 6. So I need 6 bonding groups attached to this central atom. So when you look at this, the name for this, if you were to draw faces and turn this into a solid 3-dimensional object, it would have 8 sides. 8 sides is called an octahedron. It's kind of like that. So we call this electron pair geometry octahedral. So here we have an octahedral electron pair geometry. And as you can see, as I rotate the molecule, you can see there's a high degree of symmetry here. I'm getting the same thing. Whenever I rotate this 90 degrees, I'm getting the exact same molecule coming out of this. So this one's actually a little bit easier to visualize than the 5, because here everything's at 90 and 180 degree angles. Everything is identical. All of these outer positions are identical. So being there's no lone pairs, as we've seen before, when you have no lone pairs on that central atom, your molecular geometry must match your electron pair geometry. So if I go ahead and show that, we're looking at an octahedral molecular geometry again. In terms of looking at the bond angles, we already said what the bond angles are. We have a whole bunch of 90-degree angles, as well as, if you look at the opposite ones, they're not listed on the screen, but outer, central, outer. Well, you also have 180-degree bond angles as well. Again, we're going to skip the hybridization for right now. When we look whether this molecule is polar or nonpolar, being all of these outer atoms are identical. All these outer atoms are identical, and they're equally spaced apart. Well, then we're looking at this being nonpolar. We can kind of show that. This top one, this bottom one would cancel off. The one on the left would cancel off with the one on the right. Ones that are kind of eclipsed right now, if I show them a little bit more, the one that's coming out at you is going to get canceled out by the one going back into the screen. So this one would be nonpolar if all of these outer atoms are identical. Now, If they weren't all identical, then there would be a chance for this one to potentially be polar. Remember, your nonpolar polar, a lot of times they're going to depend upon what's going on specifically with those outer atoms. So that's our first case of dealing with 6 electron groups. I'm going to go ahead and take everything off so we can build our next molecule. Our next molecule still will have 6 total electron groups. So our next molecule that we're looking at for 6 electron groups is going to be ICl5. So when you're looking at the Lewis structure for ICl5, you're going to see 6 electron groups. Of those 6 electron groups, 5 of them will be bonding groups. You'll end up with 1 lone pair. Let's go ahead and build this. I'm going to get my bonding groups in. 5 bonding groups, 1 lone pair. So if you kind of look at this to start off, 6 electron groups is always going to give you an electron pair geometry that's octahedral. The electrons are still situated in the same geometric pattern that they were before, in that octahedral, go ahead and put that up, in that octahedral electron pair geometry. What's different now is now I have lone pairs, and for the molecular geometry, I'm really just looking at where are the atoms at. So I'm going to rotate our molecule a little bit to help show you the name that we use for this particular molecular geometry. For this molecular geometry, you can see that the purple ball, the central atom, and these 4 outer atoms in the middle are kind of all in the same plane. It's kind of like they're forming a base of a pyramid with the peak of the pyramid up here. So I kind of have that pyramid type shape, but here I have a different base of the pyramid. Here, the base of the pyramid is square. So the name for this specific molecular geometry is square pyramidal. You can see the base and then the peak of that. We kind of look at the bond angles that are present here. We're going to have the same bond angles that we saw before. There's going to be a bunch of 90-degree bond angles. Anything here going up to that top one would be 90 degrees. If I rotate the molecule a little bit, there's also, again, not listed on the screen, but there's also 180-degree angles as well from these atoms that are directly opposite one another. So here's what we're looking at for ICl5. We're looking at square pyramidal for this molecular geometry. And now trying to decide if this is polar or nonpolar, we have to ask ourselves, will everything cancel out here? And try to arrange the molecules so we can see it. Well, if we look at the outer atoms that are forming the base of the pyramid, well, this one on the left cancels out with the one on the right. The one pointed out at you is going to get canceled by the one pointing away from you into the screen. I definitely don't have anything to cancel off this one on top. So in this case, whenever you're looking at something that's square pyramidal, you're looking at a polar molecule for this. So this one's going to be polar regardless of what's happening with these outer atoms. If I go ahead and take off everything, we can do our very last one that really completes the entire Vsepr set. And this one is XEF4. Again, this is another molecule that has a noble gas. Again, you're seeing a large noble gas paired with a very reactive halogen like fluorine. So for XEF4, when you look at that Lewis structure, you're going to see 6 electron groups. Of those 6 electron groups, 4 of them are bonding groups with 2 lone pairs. So let's go ahead and build that. Get my 4 bonding groups in here. And now I'll make my 2 lone pairs. So here, for this electron pair geometry, remember, 6 electron groups, 6 total electron groups is always going to give you that octahedral electron pair geometry. That's the only thing you have available when you have 6 total electron groups. That provides the maximum space. In terms of molecular geometry, though, look at what happens with the lone pairs. Notice how the lone pairs got put opposite of each other. The reason why that the lone pairs get put opposite of each other is that provides the maximum amount of space for those lone pairs. Remember, we're always trying to give the electrons as much space away from another electron group. It's even more important for lone pairs that we do it. So that's why these got put in opposite positions of each other. So kind of arranging the molecule here, I'm trying to position it in such a way that you can see this is a very flat molecule. If we're just looking at the molecule itself without the lone pairs, you can see that's a very, very flat molecule. So this molecular geometry that we're looking at, we call square planar. It's forming a very flat structure, very planar structure that has a square as kind of its key feature. We look at the bond angles. Again, if I show the bond angles, remember bond angles is what happens between outer, central, outer. I see I'm going to have a whole bunch of 90-degree angles. I rotate the molecule. I'm also still going to have those 180-degree angles that this particular simulation doesn't show. But here I have my square planar molecular geometry with 90 and 180-degree bond angles. So again, if I kind of rotate the molecule, kind of looking top down on this molecule, trying to decide if this is polar or non-polar. And again, for polar, non-polar, you have to ask yourself the question, does everything cancel out? Do all the individual net poles cancel out? And in this case, they do. Here, all of my outer atoms are the same. In this case, there's a fluorine on the top, gets canceled out by the fluorine on the bottom. They're 180 degrees apart. They're equally apart. Those are going to cancel out. The left and the right are going to cancel out in that direction as well. So everything is going to completely cancel out. This one's going to be non-polar. Now remember, polar non-polar really matters on what your specific atoms are. If I were to change one of these atoms, if I were to replace one of these atoms with a chlorine instead of a fluorine, well, then that would change this molecule into being polar, because now I wouldn't have equal strength poles here that would cancel out. Even though they're equally separated, I wouldn't have those equal strength poles that would ultimately cancel out from one another. So here's what we're looking at for our last molecule, our square planar for our molecular geometry. We have 6 electron groups, 4 of which are bonding, and 2 lone pairs. So this molecule kind of completes the sequence. We went all the way from 2 electron groups up to 6 electron groups. And again, at this stage, what you want to really be seeing is that each, look at your Vsepr tables for this, each differing number of electron groups corresponds to a different electron pair geometry. 2 electron groups, always linear electron pair geometry. 3, trigonal planar. 4, tetrahedral. 5, trigonal bipyramidal. 6, octahedral. That's always going to match up onto it. 2, linear. 3, trigonal planar. 4, tetrahedral. 5, trigonal bipyramidal. 6, octahedral, for matching your number of electron groups to a specific electron pair geometry. The other thing that you've seen in this video, just like the first video, is that when there are no lone pairs on the central atom, when that central atom has no lone pairs, you're always going to see the molecular geometry match that electron pair geometry, because all of the different positions are covered by bonds. There's going to be an atom at the end of each one of those electron groups. So those are 2 things to really kind of look at. The other thing you really want to look at is whether something is polar or non-polar. Remember that you have to analyze on a case-by-case basis, making sure you're seeing, does everything cancel out, or do some things not cancel out? So what I highly, 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 highly recommend you do, you can stare at these sheets all you want, but that doesn't get you a good feeling for how these molecules actually work. I strongly, 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 strongly encourage you and highly recommend that you go into either this program that I've been using or a different one and build these molecules to really look at that and get an understanding of what's happening with these three-dimensional shapes. Now notice in these two Vsepr videos, we skipped the hybridization part of that. That's going to come as a separate video next week.